Hello, good night. My name is Diego Matias Toledo Garcia, and today I'm going to present the damped harmonic oscillator project and the oscillatory behavior in fluids and shock absorber application. First of all, the study of damped harmonic oscillators provides fundamental insights into dynamic systems across physics and engineering. This investigation examines the oscillatory behavior of a mass spring system under varying damping conditions, with particular focus on fluid viscosity, effects, and practical applications in automotive suspension systems. Through experimental analysis and theoretical validation, we demonstrate how these principles inform the design of shock absorbers, using a Nissan Suru as our case of study. The objectives of the problem were 4 points. First, study how damping affects oscillatory motions in a mass spring system submerged in water and oil. Secondly, using amplitude time data to calculate the damping coefficient and the constant of critical damping. In third place, analyze the influence of mass and fluid viscosity on damping. Lastly, applying the results to design a shock absorber for a Nissan Suru 3. Damped oscillatory motion follows Newton's second law, incorporating both spring force and damping force. Three damping regimes exist: underdamped, critically damped, and overdamped. We use logarithmic decay to extract y from amplitude versus time graphs. The objective of this project was to get an critically damped situation for a correct shock absorber. Experiment and results. The experiment employed a mass spring system submerged into fluid media, water and oil, to create contrasting damping environments. Using tracking software, we precisely measured the amplitude decay over time for approximately 10 oscillations in water and just 3 oscillations in oil. This quantitative data confirmed the theoretical expectation that higher viscosity fluids induce greater energy dissipation. The logarithmic relationship between amplitude and time yielded the damping coefficient with oil, producing a significantly steeper decay slope of about 0.42 seconds compared to water that equal to zero point 0.1. The system's behavior is governed by the second-order differential equation, where critical parameters include the damping ratio, natural frequency, and three distinct regimes emerge from the analysis. Like we said, underdamped, critically damped, and overdamped. In the experiment, we use, as I said, some logarithmic operations to get the critical masses for each one of the fluids, obtaining for water 0.58 grams and for oil 3.15 grams. Now, the real-life application for a shock absorber for a Nissan Suru. First of all, we needed to load the distribution. The total vehicle mass was about 968 kilograms, which means each shock absorber must absorb 242 kilos. So the corresponding force should be of about 2,372 newtons. Then, getting the spring constant using the formula that the spring constant equals to force divided by compression, we obtained that the critical damping constant is of about 47,408 newtons over meters. Finally, we had to calculate the damping constant for critical damping. For a system to be critically damped, the damped constant B must be satisfied by the next equation. B equals 2 times the square root of K multiplied by mass, obtaining the number of 3,389.7 Newton seconds over meters. This study successfully bridges theoretical physics with practical engineering. The experimental results validated The predicted exponential decay patterns while demonstrating viscosity's profound impact on damping efficiency. The automotive application particularly highlights how critical damping parameters can be precisely calculated to optimize suspension performance. These findings not only reinforce fundamental physics principles but also demonstrate their direct applicability in solving real-world engineering challenges, from transportation system to structural dynamics.